we are focusing on pretty much just anything involving the idea of infinity with this. So in our first lesson with limits, you're confronted with two situations. Here's where we're going to really go into detail of the difference between as they approach infinity, as well as functions that tend towards infinity in certain circumstances. So again, you're going to see some different types, and basically whether we're talking about infinity as the limit or infinity what it equals, that's where we're going here. So they provide us some lovely graphs. It asks us to use the graph of f and then g. Oh man, it goes back and forth, doesn't it? So I probably need to have this as one page. Well, I'll have to bounce back and forth because I want room to write. I forgot that this isn't all f right here. So, okay. Use the graph of f and g shown below to compare and contrast behaviors involving infinity. Then write your discovery and definition. So right here is f. Down on my next screen is going to be g. So I'll just flip back and forth, I think. The limit as x approaches 4 from the left of f of x is what?
Infinity.
Because it did say left, didn't it?
Yeah.
Infinity. Sorry, I got ready to tell you were wrong because I was looking at the wrong side. Now let's do the one right below it. The limit as x approaches 4 from the right, which is what I was looking at, of f of x is negative infinity. Now, look at g. G asks us the limit as x approaches 1 from the left is what?
Negative.
It's going to be negative infinity.
Yeah.
And then the limit as x approaches g, or x approaches 1 from the right.
Infinity.
And that's going to be positive infinity, yes?
Yeah.
Now, what are you noticing that they were focusing around in both cases here?
Infinity. Asymptotes.
Okay, but they both had to do with vertical asymptotes, right? So the discovery here is that a vertical asymptote occurs if one-sided limits are unbounded. So basically a vertical asymptote is occurring if you have one-sided limits like the left and the right of 4, and their results are unbounded, so approaching positive or negative infinity. Okay? And that's the idea of how can I look at a limit and know what's going on in the graph? So a vertical asymptote occurs if one-sided limits are unbounded. So officially, so you'll notice right here, the definition we're putting is for an infinite limit. Down below, we're going to talk about a limit at infinity. So an infinite limit is what we are just looking at, and that was as x approaches c, as x approaches some number, the limit will either approach positive infinity or negative infinity, and thus a vertical asymptote. So that's the idea of what is an infinite limit. As x approaches c, the limit will approach either positive or negative infinity. Positive infinity or negative infinity. And I could say, I mean, officially what they, remind us. You have an infinite limit. limit, excuse me, an infinite limit, so a limit that equals positive or negative infinity, that's going to be a vertical asymptote. Okay. Okay, bottom boxes. The limit on f as x approaches negative infinity. So you're up on f now. The limit as x approaches negative infinity.
Would just be the slope of whatever line that is. Oh, I'm on G, sorry.
Okay.
Oh, yeah.
Bounce back up to f.
-2.
Are we there now?
Yeah.
As x approaches negative infinity, it's following that horizontal asymptote out at -2. And then as x approaches positive infinity on that same graph,
Yeah.
same thing. It's just approaching -2 from the underside, right? Instead of the top side. Okay, now you can look at g. What about the limit as x approaches negative infinity of g of x?
This is where I said, would it be like the slope of the line? I had to move it and just say -infinity.
Now, at least I understand why you're saying. I was like, slope of the line? What are we talking about? But, okay. Well, the slope of the line, we don't exactly know it, but I wouldn't argue the slope of the line because that's a finite number. And what's going to happen? This asymptote's going to infinitely keep going down at said slope, yes?
Slope's infinite.
No, the slope is a set number. Like this looks like to me it has a slope of -1/2. Or excuse me, positive half.
-2 on the last two, so probably.
Because those were approaching a horizontal value. They were approaching the y value of -2. This graph is going to keep going down and down farther. So what y value are we approaching? As we're going down and down farther, we're approaching that negative infinity. Anytime you have, that is what I call a slant asymptote. Okay. The slope is good for some things, but in this case, it's going to continue infinitely down, so negative infinity. On the other end, then, the limit is g of x as x approaches positive infinity of g of x. That's following the slant asymptote up, so we're looking at positive infinity. Now, we kind of had two different things here, right? But in both cases, it was as x approached positive or negative infinity. And the idea is the limit will either approach a y value, like it did with the horizontal asymptote, or it will be unbounded. And being unbounded is like it was with the slant asymptote. So we can say that as x approaches plus or minus infinity, the limit will approach a y value or will be unbounded. Okay. If it approaches a y value, realize that is definitely a horizontal asymptote happening in that scenario. Okay. Trying to think, would the unbounded have to be a slant asymptote? And it wouldn't have to be. So by definition, the limit at infinity is the whole idea of what we just said as x approaches positive or negative infinity. This is really just rewriting the same thing. The limit will approach a y value or will be unbounded. Can I just draw an arrow? I thought they rephrased it a different way, but they didn't. So it's the same thing there. Okay. Your favorite words. In pre-calc, you learned some basic truths about rational functions. So first of all, when I talk about rational functions, remember they're the ones that are fractions. Okay, they're the ones that we are, like everything on this screen right here. They're the fractions. Now, before we look at those examples, we've already talked about this. When a factor canceled from the denominator, a what occurred? And I'm actually just going to put whole here. I do agree. It is a removable discontinuity. I'm not going to disagree. That is true. Okay. When a factor would not cancel from the denominator, a what occurred? What type of asymptote? A vertical asymptote. Okay. Yeah, I know. Well, and I think here, this one was specifically referencing pre-calc. However, in pre-calc, actually in Algebra 2, I taught removable, non-removable.
That was a while ago.
So, I mean, it's not, Okay. Example 2. Use the previous equations to find the one-sided limits analytically. So, basically, I think, are we answering some of the... Yeah, these are the same equations from the previous page is what they're saying. But we're going to do them without the graph. So, the limit as x approaches 4 from the left.
First we need to factor the top.
Should what?
Factor the top and the bottom again.
Yeah, we should do some factoring. Now, the top looks ugly, but what do you notice about the top?
No. Let me try to do it on my own.
Oh.
Okay.
I'm not allowed to talk yet?
No, because the ones that there's something on the end, I'm still trying to get down there.
Okay, but don't take a look at it first.
Factor on 2.
Uh-huh.
Yeah.
I'm like, wait, you're trying to go the wrong way. If it was a regular one like that, I would, but I'm going to factor out actually negative 2. Sorry, that is the reason I stopped you there, though, because I...
Now let me get it.
How about I'll do my factoring up here, you do your factoring, we'll meet in a moment.
Before I write it down.
Check and see if yours agrees with mine. And actually, I'm
It was on the right thing, but it wouldn't have because I was still trying to do 12.
so you were struggling.
Well,
or had it actually worked?
It would have worked with like 2 and, no, it wouldn't have. I was going to do 2 and 6. That would be Did I? Yes.
Okay, there's where I'm at. Okay. If we're caught up on factoring, what's our next plan?
Again, 4. Again, 4.
What happens when we do that?
Find out.
Oh, we have a 0 on the bottom.
We'll get 0 on the bottom.
Do we get 0 on the top?
No.
No. So we get some number over 0, which is kind of you have to do some more investigation type thing. Okay. I don't want to automatically say does not exist because it could exist. Okay. what limit was this? The limit as x approaches what?
4 from the left.
4 from the left.
So 3.9.
Yeah, so I'm not opposed to plugging in 4, even though it says 4 from the left, until this happens. Then when this happens, I'm like, okay, we got to back up a step. Officially, it was approaching 4 from the left, so let's plug in something from the left. So, -2 times, I'm going to say 3.99, or 3.9, whatever, plus 3 over 3.99 minus 4. So now basically, I may have -2 times 6.99 over -0.01.
So it's just going to be infinity.
What?
It's just going to be infinity.
Okay. You've got a number that's around -4. Well, first of all, negative divided by negative is a positive. So basically, you're dividing a number like 14 divided by 0.01. And if we put in more decimal places, it'd be a number like 14 divided by 0.000001. And so, yes, this is going to tend towards infinity. Now, officially, I think we did this limit on the graph. It was the very first limit of the day, and guess what? Our answer matches. Okay, B.
Like, difference is the other one would have been 2 and we had -2.
No. The very first A, yes, on the front page.
Yeah.
This is the F graph. The limit as x approaches 4 from the left, is what we just did.
So what does the 2 got to do with anything? And we canceled out. That's usually like a whole.
The GCF of -2?
No, the x minus 2. We canceled out.
It didn't matter in this case. So here's the deal. In all reality.
So it only matters when it matters. It doesn't matter when it doesn't matter.
Okay.
Exactly.
Okay. Listen. If we would have plugged 4 in, we still would have gotten 0 on the bottom. We still would have had to do more work. But I'm going to tell you, plugging 4 in would have been more difficult in a scenario when you had not factored. Factoring was still beneficial. Okay? Now, I'm going to jump to, this is the same equation, right? It's just from the right. So I'm going to jump to our factored canceled form of -2 times x plus 3 of x minus 4. You can see the same thing's going to happen, yes. We can't just plug in 4. This is a number from the right, so 4.01. So I end up with -2 times 7.01 divided by 0.01. Essentially, I end up with -14 divided by a positive 0.01. The difference now is?
The negative on top, so it's negative.
Yeah, where do you go for negative, Fendi? Did I do that right?
That's what I did. That's what I did. What would be different?
I just have a mistake in my answer key in my work. Not my answer, but my work. That I have it as, well, it's about -14 over 8 is what that looks like. And I don't know why, like 4 plus 4 instead of 4 minus 4. So I don't know what I was doing. Okay. Continuing along. Okay, C. Limit as x approaches 1 from the left. Thoughts?
Already take out the 2 on the denominator. I don't know what's going on the top.
And that's the top factor. Top doesn't factor. You can take a denominator out on the bottom. Or a denominator, GCF. I'm not sure it's really going to, help a whole lot or be worth it. I mean, the numerator is the difficult part. That's the part that's annoying. Okay. Now, whether that denominator is factored or not, if we plug in a 1, my denominator is going to be 0, isn't it? And so this was as x approaches 1 from the left. And so here's the deal. Think about, okay, how am I going to do this without a calculator? So what x value would you probably use? Something like 0.999, right? We don't have to have exact numbers here. If we plug that in, we just generally have to decide, how do I want to say this? In terms of, because we can see, what's my denominator going to tend towards? 0.999 minus 1, that's almost 0, but it's a negative, yes? 2 times a negative is still going to be a negative, but it's going to be a very small number, isn't it? So I want you guys to think that that's going to be a negative, and it's going to be a very small negative. Whereas, what about on top?
It's going to be positive.
When you square something positive, okay, and then subtract 2 times something positive, well, I would say x squared is normally bigger. I don't know about in this case, but then you also have to add 5 on. You're squaring something and adding 5. That's probably going to end up bigger than taking off. So that's going to be a number that is approaching, that is positive, and it's approaching a bigger number, yes? So if you have a number that's getting bigger, divided by a number that's getting smaller, we're thinking infinity. In this case, because it's a positive divided by a negative, we're looking for a negative infinity. So that's the idea of how you reason it without having a calculator at your side. Okay. This would be going 1 from the right. What changes?
1.01.
Okay. Plug in like something like 1.01. The top? Still going to be a positive, and that's a number that's going to be getting larger and larger. What about the bottom? 2 times something a little bit bigger than 1 minus 2 is going to be a positive. It's still going to be a really small number, but a positive. A positive divided by a positive is a, I don't know why I just wrote positive infinity, but I did. Okay?
There was some positive infinities in the answer too.
Huh? Oh, regular infinities and positive?
One, yeah. No, I said negative because I keep thinking, I don't know why, that it's like 2 times x minus 2. Like 2 parentheses x minus 2.
Oh, as opposed to x minus 1 then. Okay, moving on. Okay. Definition and justification of vertical asymptotes. So this is just going back to our 2 main types of discontinuities. If your fraction is of the idea that you have a non-zero divided by a 0, okay? What they're saying there is when you have that 0 in the denominator, you're looking at that's going to be an example of a vertical asymptote. Okay, and that's what we were just kind of looking at, where we were getting 0 in the denominator. Excuse me. That's going to be an idea of a vertical asymptote. This one over here, when it's a 0 divided by a 0, I know we talked about indeterminate forward, but in this situation we're referring to if there's that factor of 0 and 0 that can cancel, we're looking at a hole, a very strong possibility of a hole. So location of a hole or a point discontinuity. Hey, you write what you want. Okay. Notice the comment here. We were talking about, the language that you guys were annoyed at of seeing in, the homework and stuff. In calculus, you must use new language in order to justify. So you have to learn to be able to use the appropriate language. Limit definition justification of a vertical asymptote. And so I'm going to write it down, then we can talk about it. If the limit as x approaches c from the left of f of x equals either positive or negative infinity, or the limit as x approaches c from the right of f of x equals positive or negative infinity, then x equals c is a vertical asymptote. Okay. Sorry, I was trying to avoid that, but I couldn't. Okay, so the idea there that if you're approaching that value and your limit goes to positive or negative infinity, either you're approaching from the left or the right, that's going to be a vertical asymptote. If you're approaching some solid numerical value. Okay, so that's your official justification. Here we go. This is one Logan wants to factor on his own. Use the function below to find any vertical asymptotes that exist. Justify your answer using limits. I would factor the denominator earlier rather than later. Just because that can help. It won't always, but it can. I waited to fill that in so we could talk through it, or no?
I just keep thinking that we're going to have to use that middle, so the 9 was the middle.
So the middle, where you use the middle, is use it as a check at the end. Do my outsides and my insides give me that 9. So 10x and minus 1x. That's...
Just do like, does it work too? It's just like 5, 2, and 1, 1 equals 9, like all the coefficients.
I don't know. I can't 100% say that. Okay, so what's going on here? Okay, there's a hole now. It didn't really ask us about holes, did it? It just mentioned that use the function below to find any vertical asymptotes that might exist and justify using limits. Is there any vertical asymptotes?
Plug in, so.
Well, but just
So
right.
2, yeah.
Okay, so just based on the fact there'd be a hole at -5. There's a vertical asymptote at 2, just based on what we know about rational functions, yes? And we're specifically talking about rational functions. So, I can say at x equals 2, there is a vertical asymptote. Of course, I just looked down my notes and I abbreviated there, but there's a vertical asymptote because now okay, we haven't found these limits already yet, have we? Is this our first time working with this equation?
I believe so.
Okay, so we need to figure out, because the limit as x approaches, so we have to look at 2 from both sides, 2 from the left of h of x is hopefully either positive or negative infinity, and we need to look at the limit as x approaches 2 from the right of h of x is either positive or negative infinity. And for some reason I did the chart at in the bottom corner here, so
How are you going to know?
well, that's what we're going to have to figure out. So x values, what x values do we need to check? 2 from the left would be checking like something like 1.9999, right? 2 from the right would be checking something like 2.0001. So you can use the simplified version here of 2x minus 1 over x minus 2. What do you know about a number when you put in a number just smaller than 2 and subtract 1 on top? Is it going to be a positive or a negative? It's going to be a positive, right? Divided by a number on bottom, it's going to be negative, but it's also going to be a very small negative that's getting smaller and smaller and smaller, right? And so what's this side going to tend to? That's going to represent negative infinity. If we think about plugging in 2.001, well, the top is still going to be a positive, and that's a number that's getting larger, whereas the bottom, 2.001 minus 2, is almost 0, but it's positive, right? Just becoming very much smaller. So positive divided by positive makes this equal positive infinity.
That's our answer.
Yeah, and that's just an indication of, using appropriate language, proper language. Like that's officially how you can state it, is showing those two limits. Showing that they either both approach positive infinity, negative infinity, or opposite infinities. Okay?
Six minutes.
Yeah, we still have a lot of notes to do, don't we?
Yep.
Where's my halfway point? Did I need to make it through? Yeah.
This page.
I think I make it through this page, but let's at least talk about one, I guess. Okay. So, exploring limits at infinity in order to differentiate between the two conditions. So, from pre-calc, we talked about in behavior. And if you go back to Algebra 2, this is where I use the vocabulary like up and down and up, down and down. Like I use that type of vocabulary there. In pre-calc, I don't think we use that same vocabulary. There's more infinities and whatnot, but what do we have here? As we look at example A, the limit as x approaches infinity. It's x squared minus 4 times x squared plus 3. If you were to FOIL this out, what would be my high power?
X squared. Oh, the FOIL it out, yeah.
It'd be x to the 4th, yes? So x to the 4th means this is going to be some type of, yep, I'm not there yet, but yep. I was going to use the word quartic polynomial, and quartic polynomials are like parabolas. Yeah, they go the same direction. Anything that's even goes the same direction. This is positive, so it's whether it's like an up like this or whether it's like a W type shape, it's going to be having that type of end behavior there. Okay? Now, what did I write out here? End behavior model, leading coefficient. I don't know. So, as x approaches infinity, what's this graph going to do?
Go to infinity.
It's going to go to infinity because either way you look at this, this is going to be, if we go back to Algebra 2 terminology, not good pre-calc terminology or calc terminology, but it's going to be going up. Now, I'm trying to decide how I want to write this because I don't like how I have this written in my notes. So, I mean, it's going to go to infinity is definitely what I would say.
Say limit as x approaches infinity equals infinity.
Yeah. So, I'm just going to write end behavior here because that's what it's called when you look at the type of function there. What about B?
So it would be x to the 3rd, so trinomial.
Cubic is what we usually said.
Cubic.
Yeah. X to the 3rd is going to be a.
Since it's negative. Or no.
So x cubed. My ends are.
So as it goes to negative, it's going to be down and then up.
Yeah.
So as it goes to negative infinity, it's going to be negative infinity.
Since this is a posit cubic, it's going to be something, I don't know what it looks like,
Yeah,
but
I think
it's going to be down and up, right? Again, if I resort to that Algebra 2 terminology, it's going to be down and up. And then, since it's asking about as x approaches negative infinity, our answer is going to be also negative infinity. And it does say to explain your thinking. That's the part I'm not doing a very good job on, but okay. So I guess when I say negative down and up, that's what I should be looking at there. Okay, so those are actually going quicker than I thought they were. Shall we talk about C tomorrow?
Well, so wouldn't it be the highest power would be the first?
Well, this one's a fraction, so it's
Yeah.
more like, think about your horizontal asymptote rules. When the powers are the same versus when the power is bigger on top or bigger on bottom. There's 3 different horizontal asymptote rules there. So.
One of them 0, one of them's, is it infinity 0, negative infinity, or
No.
infinity undefined?
One of them's 0. One's no horizontal asymptote because it comes to slant asymptote, and the other one is the coefficients when the powers are the same. So we'll look at it tomorrow.